I'm going to wait a couple more minutes. See if anyone else joins. Okay. Hello to those of you on Zoom. Can you hear me?
Yep.
Okay, thanks. All right. Right, I'm going to share my screen. And turn on the projector. Last time we looked at alkenes and alkynes, and we looked at the structure and properties and nomenclature of alkenes and alkynes. Like alkanes, alkenes and alkynes are nonpolar compounds. They're insoluble in water. They are less dense than water in the liquid phase. They are more reactive than alkanes, though. Alkanes are generally unreactive. There's only a few things that alkanes will react with. Because of the double or triple bond, that's the active site, that's the functional group. Okay, so to review the naming of alkenes and alkynes. Okay, if we have something like this, okay, the longest chain that contains the double bond, that contains both carbons of the double bond, is the parent compound. That's 1, 2, 3, 4, 5, 6. If I go this way, if I go this way, it's still 3, but my substituents would have a higher number. Okay, so this is 3-hexene. You could also call it hex-3-ene. This is the newer method. And then the other substituents, okay, we have an ethyl on 3, so that's 3-ethyl, 2-methyl. Okay, we separate numbers from letters using a dash. We separate numbers from each other using a comma. The double bond takes priority over alkyl substituents like methyl or ethyl. Okay, if the double bond were not there, this would be carbon number 1. And this, it would be 2233 tetramethyl. But because the double bond is there, we want to give it the lower number. 1, 2, 3, 4, 5, 6, 7. That's 7 is heptene. And it would be 2 heptene, because the double bond is between 2 and 3. And it would be 5, 5, 6, 6, 5, 5, 6, 6, tetramethyl 2-heptene or hep2ene. And double bond takes priority. Got a couple more. Coming in. Okay. Right, if we have a triple bond, right, the triple bond has a linear geometry. Okay, these 4 carbons are all on a straight line. Each one of these represents a carbon. Okay, so we would have 1, 2, 3, 4, 5, 6, 7. Again, this would be hep. And since it's a triple bond, it's heptyne. And it would be, okay, again, this would be 2-heptyne. The newer method is hep2ine. Okay, a couple of other aspects of naming that I want to review. I'm going to go ahead and erase this. One is if we have a cyclic alkene, okay, such as this one. Okay, so say we've got something like this. Okay, the double bond defines where carbons 1 and 2 are. Okay. We will cover other functional groups that are higher priority, okay, things like alcohols and ketones and so on. Those are higher priority than the alkene. As long as we just have these alkyl substituents, double bond takes priority. Okay, so double bond is between 1 and 2. And 1, 2, 3, 4, 5. We go this way. 1, 2, 3, 4. Okay, so this is 4. And what's this group here? Isopropyl. Yeah, 4 isopropyl. 4 isopropyl cyclohexene. Okay, you can say 1 cyclohexene, but you don't have to. It's understood that it's between 1 and 2. The double bond is between 1 and 2. Okay. Cyclic alkynes are unusual. You have to have at least a 9-membered ring to have a triple bond. Okay, because of the requirement that these 4 atoms all have to be in a straight line. Okay, the last thing I want to say about nomenclature is if we have more than 1 double bond. we have more than one double bond, then if we have two double bonds, then it's a diene. And we need to specify the positions of both of those. Okay, so this is 1, 2, 3, 4. Okay, that's hexane. And okay, the double bonds are between 1 and 2 and between 4 and 5. So this is hexa 1, 4 diene. Okay, diene, 2 double bonds. Okay, if we had 3 double bonds, it would be a triene. If we have a cyclic polyene, okay, remember if we have just one double bond and nothing higher priority than a double bond, it's implied that the double bond is between 1 and 2. If we have more than one double bond, we do have to specify where they're located. Okay, so an 8-membered ring is what? Cyclo octane, right. Okay, so this is cyclo octane. Okay, there's 2 O's. And there's 3 double bonds, so this is so that's cycloocta 1, 3, 5 triene. Cyclo 1, 3, 5 triene. All right, chapter 4 has just one reaction. Chapter 5 has all of the other reactions of alkenes and alkynes. Okay, and this particular reaction that they talk about in chapter 4 involves the acidity of terminal alkynes. Okay, terminal alkynes is triple bonds at the end of the chain. All right, so if I have something like this, okay, it turns out that as far as CH bonds go, this CH bond is, relatively speaking, unusually acidic. The pKa is about 25. Okay, if we wanted to sure I'm still on screen, okay. If we wanted to remove this proton using hydroxide, okay, that's not going to work because water has a pKa of 15.7. Okay, the smaller the pKa, the stronger the acid. Okay, when we have an acid-base reaction, it's always stronger to weaker. Okay, so this wouldn't be favorable. The reverse reaction, though, would be highly favored. Okay, if we had this anion, we reacted with water, it would immediately take a proton from water. Okay, so this doesn't work, but if we use the conjugate base of ammonia, okay, which is NH2 minus, okay, plus NH2 minus. This is a salt that is called sodium amide, sodium amide. This is carried out in liquid ammonia. Liquid ammonia is cold. It's about, see off the top of my head, it's somewhere in the neighborhood of minus 35 degrees Celsius. It's a gas at room temperature. So this is carried out in a cold solvent. This works though. Okay, so this pair of electrons will grab this hydrogen. This pair of electrons will shift onto the carbon like this. Okay, sodium is just a counter ion. It doesn't do anything other than balance the charges. It's a spectator. And then NH2 minus, when it gains a proton, it becomes what? NH2 minus plus H plus is NH3, right? Okay, so that produces more of your solvent. Okay, so this works. The pKa of ammonia is about 38. Okay, so ammonia is a much weaker acid than this terminal alkyne proton. Okay, a couple chapters ahead, we will look at why this is a very useful reaction. If we have a negatively charged carbon, we can build just about whatever carbon chain we wanted. Okay, so this is a very useful synthetic tool. Okay, a couple of compounds that will not work with the NH2. Okay, if the triple bond is in the middle of the chain, okay, there's no H there, and nothing will happen with sodium amide and liquid ammonia. Okay, there's the pKa of these hydrogens would be about 50. Okay, so nothing's going to happen if you try this. If we have an alkene, okay, the pKa of this hydrogen would be about 45. Okay, and again, that's a weaker acid than ammonia, so that wouldn't work either. Okay, so that's the only reaction from chapter 4. Okay, so I'm going to begin this slideshow with reactions of alkenes and alkynes. Okay, here is a summary of the reactions. And let me get this light here. Those in the classroom can see that a little bit better. The most dominant or the most common type of reaction for an alkene, also for an alkyne, is what we call addition. Okay, notice the pattern here. Okay, we start with a double bond and we react it with something, and notice in the product there's no double bond. We've added 2 groups, one to each side of that double bond, and our product has a single bond. We're going to look at each one of these in detail. The first one is hydrochlorination, or in general, it's hydrohalogenation. We could also use HBr or HI, and we add an H to one side and a Cl to the other, and there's no double bond in the product. There is hydration. Okay, H and OH, the elements of water, add across a double bond. We get, our product is an alcohol. This doesn't take place just by mixing the alkene with water. We do have to have a catalyst. Right, we can add a halogen. Okay, X2, or X is chlorine or bromine. This time we add 2 halogen atoms, 1 to each side. And again, our product has no double bond, it has a single bond. The next one is what we call hydroboration, where we use borane or some equivalent boron compound, and we add H to one side, BH2 to the other. This product, though, is not isolated. We go ahead and convert it to an alcohol. We can also add 2 hydrogens using hydrogen gas, 1 hydrogen atom to each side. This also has a very high activation energy, and so you have to have a catalyst in order to accomplish this. Okay, just a brief review of energetics. Okay, in this graph, the y-axis is energy. The x-axis is the reaction coordinate or progress of reaction. So for a one-step reaction, we have let's go back. Okay, for a one-step reaction, on the left we have the starting materials. They have to go through a certain activation energy. They have to collide with enough force in order to react. And this goes through a transition state. And in this hypothetical transition state, there's a bond that's partially formed, a bond that's partially broken, and the energy difference between the starting materials and the transition state is what's called the activation energy. In this example, this is an exothermic reaction because the energy of the products is lower than that of the reactants. Okay, so heat is given off to the surroundings. Okay, this is a definition of different parts of the curve. The transition state is an unstable species of maximum energy formed during the course of a reaction. A transition state is so short-lived it's very difficult to observe. The activation energy is the difference in energy between the reactants and the transition state. The activation energy actually does determine the rate of a reaction. Okay, lower activation energy will result in a faster reaction. So if activation energy is large, very few molecular collisions occur with sufficient energy to reach the transition state. But if the activation energy is small, then you have a faster reaction. There's more collisions. Also shown is the heat of reaction, the difference in energy between reactants and products. In that example, it was an exothermic reaction. If we did the reverse reaction, it would be endothermic because going backwards, the products would be higher energy than the reactants. Okay, here's a two-step reaction. Here's a two-step reaction. And this local minimum is what's called an intermediate. Okay, this is an intermediate. An intermediate is something that is formed in one step and then it's consumed in a subsequent step. The intermediate does not appear in the overall reaction. All right, since this is a two-step reaction, we have two activation energies. The first one is much higher than the second. And so the first step is the rate determining step. Okay, that'll be the slowest step because it's the highest activation energy. The first step is endothermic. The second step is exothermic, and the overall reaction is exothermic. Okay, we're going to look at each one of these reactions in terms of a reaction mechanism. A mechanism is a step-by-step description of what's happening. It's the order of bond breaking and bond forming. And it may include the role of a catalyst. It may include the role of a solvent, okay, if one is present. A mechanism typically does not list reagents or experimental conditions. Okay, reaction mechanism is not something that can be necessarily proven, but it needs to be consistent with available evidence. This first bullet point is very broad: design experiments that will reveal details of the reaction. Some of the things you can look for, you can determine the rate law experimentally. For example, you can use the method of initial rates, see if it's first order or second order. You can add a suspected intermediate, see if that changes the reaction, or you can remove a suspected intermediate as it's formed, or observe it. Okay, and then you propose the set of steps, and bullet point number 4, if the evidence is consistent with the mechanism, that doesn't mean the proposed mechanism is correct necessarily, but it is the best explanation. Okay, and in this course and in organic chemistry, we use a curved arrow convention to show the movement of electrons. Okay, that's something we're going to do all throughout the rest of the course. Okay, these are some very common mechanism steps. Okay, the first one is adding a proton, or you can also look at it as transferring a proton. Okay, notice we begin the arrow, in this case, at a lone pair of electrons. We always go from high electron density to low electron density. That proton in acetic acid is low electron density. Okay, so we donate a pair of electrons from the nitrogen to that hydrogen. That gives hydrogen too many electrons, so hydrogen has to give away 2 electrons to the oxygen. The electrons moved away from nitrogen, so it was neutral, and now it has a plus charge. The oxygen was neutral, but it had a pair of electrons move toward it, so it becomes negative. Okay, here's another example. Besides a lone pair of electrons donating as a donor, an alkene or an alkyne can donate a pair of electrons. Okay, so those are the two main species that can donate electrons, a lone pair or a multiple bond. Okay, you never draw an arrow starting from a plus charge. Okay, it always goes the other way. Okay, so here we have the hydronium ion. The double bond, a pair of electrons in the double bond picks up a hydrogen. Okay, so that pair of electrons was used to form this CH bond. So that leaves an empty spot on carbon number 2. So that's now a carbocation. Hydronium lost a proton, so it becomes water.
Would it matter which one picks up the hydrogen?
In this example, since it's symmetric, no. But if it's not symmetric, it turns out that yes, it does. Okay, the question was, does it matter which side the hydrogen goes to? Okay, so this is adding a proton. Okay, this is the reverse of what we just saw a few minutes ago. This is removal of a proton. Okay, so if we go the reverse direction, something with a lone pair or a multiple bond can pick up a proton. Okay, pattern 3. Reaction of an electrophile and a nucleophile to form a new covalent bond. An electrophile is also called a Lewis acid. Okay, definition of a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor, also called a nucleophile. Okay, so phile means love, so electrophile is something that is seeking electrons, so it's electron deficient. A nucleophile is a species that's seeking a nucleus, a plus charge, so it has an excess of negative charge. Okay, so here's a good example of the reaction of a nucleophile with an electrophile to form a new covalent bond. So chloride is the nucleophile. It's the Lewis base, the electron pair donor. Okay, we start from the base, and it attacks this positively charged carbon, donates a pair of electrons, and it forms this covalent bond. The fourth common mechanism pattern is what we call rearrangement. Okay, so in this instance, what happens is, okay, if we think of a model kit, okay, we're going to pull that hydrogen out and we're going to move it to the empty spot next to it. Okay, carbon number 3 that's pictured here only has 6 valence electrons. It carries a plus charge. And okay, so we're gonna move over that hydrogen with its pair of electrons, and that leaves an empty spot on carbon number 2. Okay, the driving force for that rearrangement is that we produce a more stable carbocation. The one on the left is what we call a secondary carbocation. Okay, this positively charged carbon is directly bonded to two other carbons, so it's secondary. The one on the right is what we call a tertiary, and it's more stable, and so that's what drives this reaction, this rearrangement. Okay, and then another common pattern, this is commonly called heterolysis. Okay, this is just the reverse of what we saw a few minutes ago. Remember where the chloride comes in and it attacks the positively charged carbon and forms a new covalent bond? Okay, well, this is just the opposite. This is where bromide leaves, taking a pair of electrons with it. Carbon was neutral, it lost a pair of electrons, so now it's positive. Bromide gained a non-bonding pair, so now it's negative. Okay, so these are the reactions that we looked at right at the beginning. And we're also going to look at the mechanisms, the steps involved in each one of these. Okay, notice the first bullet point here. This is addition of hydrogen halides. And we add H and Br. And the question was, does it matter which side H goes to? And you can see that by this product that yes, it does. And we're going to look at that in more detail. Okay, so H ends up going to carbon number 1, Br goes to carbon number 2. And then the second bullet point is addition of water. We do need a catalyst here, something like sulfuric acid. We add H and OH, and again, H goes to carbon number 1, OH goes to carbon number 2. Okay, we can add halogens to a double bond, chlorine or bromine. We get a dibromo alkane. All right. We introduce a new term, and this is what is called regioselective. Regioselective means that the reaction favors a particular positional isomer. Okay, with ethylene, since that's symmetric, it doesn't matter which side gets the H and which side gets the Cl. But with propene, this is regioselective. Propene is unsymmetric. Okay, we've got a CH2 on one side, and then we've got a H and a methyl on the other side. Okay, our product is 2-chloropropane and not 1-chloropropane. So a particular positional isomer is favored. And we can predict this using what is called Markovnikov's rule. Okay, Markovnikov was a Russian chemist. He lived in the 1800s, about the same time as Mendeleev. And in Markovnikov's rule, in addition of HX to a double bond, H adds to the carbon with the greater number of hydrogens already bonded to it. Okay, there's a couple of ways of restating that. One is when it comes to hydrogen, the rich get richer. Okay, whoever has the more hydrogens, most hydrogens, gets the hydrogen. Okay, and you probably think I'm kidding, but I'm not. When I took organic chemistry, we had Markovnikov's rule in the King James Version. Unto him that haveth much, more shall be given. Okay, so rich get richer when it comes to hydrogen, so we can predict what our product will be. Okay. Markovnikov's rule is but one example of regioselectivity. We'll see some more examples in this and later chapters. Okay, so here we have 2-methyl propene. Carbon number 1 has 2 hydrogens, carbon number 2 has 0. And so the H goes to carbon number 1, I goes to carbon number 2, and the other isomer is not observed. Okay, we just saw this a minute ago with HCl and propene. Okay, here we have 1-methyl cyclohexene. The addition of water with a catalyst is also regioselective. It follows Markovnikov's rule. So H goes to carbon number 2 down here. There's 1 hydrogen here that's implied, and then on carbon number 1, there are no hydrogens. So rich get richer. So hydrogen goes here, OH goes to position 1, and then the other isomer is not observed. Okay. So we should be able to predict what the products will be here. Let me move the camera over just a little bit here. Okay, so for the first one, and our double bond is here, and we're adding HBr. Okay, which carbon does the H go to? Rich get richer. 2. Yeah, 2 is right. Okay, and then Br goes to the other side. Okay, so H goes here, and Br goes here. Okay, I'm going to go ahead and erase this. Okay, so this is our product. Okay, adding water with a catalyst. Again, this is the same starting material. Okay, so H would go to carbon number 2, and then OH would go to carbon number 3, and there's no double bond in the product. Okay, letter C. Okay, so here we have 2,3-dimethyl cyclohexene, and we're adding water in the presence of catalyst, H and OH. Okay, so this is carbon number 1, 2, 3. So H and OH, which position gets the OH? 2, right, and position 1 gets the H. All right, so our product, okay, rich get richer. Okay, so there was an H there already, so this becomes a CH2, and then OH goes here. All right, and then the last one. The name of this, by the way, would be vinyl cyclohexane. And this is what's called a vinyl group. Okay, so which side gets the H? Right side, yeah. Oh. Okay, so BR would go here. Okay, and then this would be a CH3. Okay, I have about 3 minutes remaining. Okay, we'll go through the mechanism for addition of HCl to 2-butene. Right, and the way this works, okay, this is an example of addition of a proton. Okay, so the double bond picks up an H from HCl. This is a slow rate determining step. We used up a pair of electrons to form this CH bond on carbon number 3 here. Okay, that leaves an empty spot on carbon number 2, a carbocation. The electrons move toward chlorine, so it becomes negative. And then the last step should be very rapid because we've got these opposite charges and they attract each other. And so chloride is going to donate a pair of electrons to that carbocation and will form a new bond. Okay, and so the product is 2-chlorobutane. Okay, since this example is symmetric, it doesn't matter which side the H and which side the chlorine goes to. But the last thing I'll mention is, okay, on the previous slide, we did all those examples of Markov-Nikol's rule. And the reason Markov-Nikol's rule allows us to predict which regioisomer we'll get is because the more stable carbocation will be formed faster. And I will talk about that in more detail on Friday. Okay, and I'm gonna before I end the meeting, again, if you have questions over the material, you can email me. I have office hours. If you don't want to come to my office, I can meet you on Zoom, or we can do a tele appointment. Okay, but if you do have questions, please contact me. Okay, and I will see you virtually on Friday.